Nat Morris here from Cumulus Networks. He will talk about his open network install environment called ONIE, and yeah.
Cool. Hi, I'm Nat from Cumulus Networks. We're a startup based in Mountain View in California. We came out of stealth mode in June last year, and we have a network operating system that runs on top of rack switches in the data center. Can I see a show of hands for people that use Pixie to deploy their servers in the data center? Okay. And has anyone tried to change the firmware or jailbroken a network device at home, like a WRT router or a Linksys device at all? And anybody used U-boot at all? Or a JTAG programmer? Okay, a few people. This morning I'm going to go through ONIE, what the project's about, where it's used, what we've learned during the development, and I'll do a couple of demos of it as well. So first of all, I'll just talk about why we need ONIE in the network market space at the moment, and what it enables us to do, and what it's changing in the industry. So if we look at the landscape in the data center, the IP vendors, you see on the left-hand side we have open vendors, and on the right-hand side the ones that are closed. And by the way we mean closed in this discussion is people like Cisco or Juniper or Arista who ship a closed unit. You get the hardware with the operating system, it's all wrapped up. You just get a single binary. You don't get any source code. You don't get access to the raw hardware. And what Cumulus ourselves and our competitors in this market, like Big Switch and Pico 8 are doing, is we're trying to separate the hardware from the software to have some disaggregation. So you can pick the hardware vendor of your choice and run a network operating system on top of that. And you can switch it out at any time. So some examples of some vendors that are interested in joining this community and providing open hardware are people like Quanta, who you might have come across, who typically have built servers, or EdgeCore, and Dell are now playing in this space as well. So some of these names might not be familiar, like the Quanta or the EdgeCore, and that's because they're ODMs from Taiwan, and they normally build a switch, and then a manufacturer, like someone on the right-hand side, such as Juniper or Arista or Cisco, will purchase that switch and change the front plate and rebrand it. So you don't normally come across these vendors. And this is typically how it's always been. You've had a manufacturer like Cisco and you get this single blob. And we want to introduce this split now. So you have the hardware at the bottom, you can put on top of the operating system. And in all the cases we've seen, that's normally Linux. And then on top of that, you can install your own applications. And the benefit of running Linux on your network switch is that you can manage it really easily. You can treat it just like another server in the data center and use the tools that you've been developing for years to manage it, like Puppet or Chef or Ansible or Salt, or your own homebrew bash scripts. So the talk this morning isn't really about our network OS, but it's how do we get those operating systems onto the hardware, and how do we do it in kind of a simple manner and allow people to swap the operating system out. So this is what a typical leaf switch might look like that you put at the top of the rack. This is one from Quanta. It's got 48 10 gig SFP slots on the front and 4 40 gig ports in this example. Another model switch very similar to this would be a 1 gig switch with 48 1 gig copper ports and 4 10 gig ports. You always have a serial console port, and we tend to see those run at 1150-200 now instead of 9600 like on the kind of classic sealed units, a lot faster. And then you'd also get an out-of-band Ethernet management interface as well. And the price point on these, because this is open hardware and being sold separately to the OS, is a lot cheaper. You'd normally see this unit in single volumes for about €4,000, which is a lot cheaper than you'd normally be paying. And this is what a spine switch might look like in a big data center. In this case, this is a 32-port 40 gig unit. And you can break each of those 40 gig ports up into 4 10 gig ports with a splitter cable. So they're pretty pretty standard units. And you can see these don't normally come with any branding because you'd be getting them straight from the ODM or via a reseller. So how do we go about provisioning the switch? Well, what we've always done in the server world is we had the bare metal server at the bottom, and we've always it's come with a BIOS and Pixie in most cases to do the boots. So when Pixie starts up, it'll do a DHCP request. It'll look for some options from the DHCP server to get the file name, and then it'll go through using something like ISO Linux to do the install. So we've needed to replicate that for the bare metal market, because when you go to one of these vendors such as Quanta, you'll just get the unit. It'll come with U-boot on there, and that'll be it. It's very hard to do the install. You'll need to be talking through the user about telling them on the different hardware where the flash starts and finishes, where they can store values in the EEPROM. So we come up with this project called ONIE, which is the Open Network Installer, which we think is a bit like a Pixie boot on steroids. It's U-boot and ONIE. And we have a hardware compatibility list of devices that we've certified ONIE to run on top of. It's available on GitHub, and all the documentation and source files are up there with a GPL license. So now we've been doing this for a couple of years. We're now starting to see vendors highlight ONIE compatibility on their data sheets, which is great. And this means you can go to a vendor, and as well as getting the switch with a classic OS that it came on, maybe some kind of QNX operating system or some other kind of vendor-sealed OS, they list it as being ONIE compatible. And that means you can plug different operating systems on top of it at will. So maybe if the OS that you're running this year in the data center doesn't have a layer-free routing stack that you need, because the switch has got ONIE on there, you can just remove that operating system and install a new one that has those features. Or maybe an open OS that allows you just to run your own routing stack in maybe Python or in Go or whatever you like. And since this market is starting to get a lot of traction, we've seen one of the big vendors in January, Dell, announce support for ONIE on their switches. So in particular on the Dell S4810 and S6000 switches, you can now purchase those from Dell, and in the next couple of months they're going to be adding a feature onto their site. So just as on the left-hand side, for a few years now, when you purchase your x86 box, you can pick the network operating system. The question?
And are these the switches purchased with, let's say, over FOSS 10, or are these the old switches that have the OEMs that talk with the OS on?
Okay, so in this case,
Sorry, please repeat the question.
I just wanted to know the model.
On mic.
Okay, better. Sorry. The models you are talking about, are these the FOSS 10 ones, which Dell took over with the acquisition, or the old OEM ones, which I think
like
similar to the Quanta
SMC
ones,
boxes? No, so these are all the Dell FOSS 10 boxes,
okay,
which come with, typically they come with the Trident Plus or Trident 2 chipset in there. So in this case, in the next few months on the Dell site, you're going to see these radio buttons appear, where you can pick the old Dell OS or the FOSS 10 operating system at the top, the Dell networking OS. You can be able to pick ourselves pre-installed, or other network operating system. And that'll mean that the box comes with just ONIE on there, where you could either install ourselves, or you can install FOSS 10 or another vendor.
So, follow-on question to that. So after the switch is booted,
yep,
and the operating system is on it, and you have secret sauce that speaks to like low-level the ASICs, Trident 2 chipset, etc.
Yep.
So I guess it doesn't only need to be ONIE compatible, it also needs to be compatible to your OS to enjoy the greatness of hardware switching, right?
Yep, indeed. And that's the element that's not quite as open as we'd like it to be at the moment. Because when you're writing a network operating system that runs on top of a switch, you need to talk to the ASIC. And traditionally that's via an SDK that you'd license from the merchant silicon vendor such as Broadcom. And at the moment those aren't open. Lots of discussions underway But we're not in that kind of position at the moment. So what is ONIE? It provides an environment for the network operating system installation and discovery. It's like a pre-installed Kickstarter that sits on the box. It's a very, very, very small operating system, just a couple of meg. It's defined by its behaviors, and it's based on a modern Linux kernel and BusyBox. And it's all just written in Bash. You can see it all on GitHub. And recently, just before Christmas, it was ratified by the Open Compute project, which you might be aware of is an initiative started by Facebook, originally to put out hardware designs for servers under an open source license. And now there's people in that group that are developing network switches that they want to release the hardware designs for and the SDK in an open manner. But to be able to get the operating system onto the switch in the first place, you need a bootloader. So they picked ONIE as their bootloader of choice. So these are the vendors at the moment that support ONIE. The question?
On the slide, you said it's filled with the Open Compute project.
Yep.
Has it anything to do with the Open Daylight project? Are you aware of that?
No. So Open Daylight is a controller for SDN networks. That's completely separate to the OCP project.
Okay.
So the OCP project is about designing, say, servers or racks or power supplies to greatly reduce the cost of hardware going into the data center. And they've kind of had those elements nailed for a few years now, rolling out racks en masse and having that hardware produced. And it's now the network elements that are missing that they're having to suck up to Cisco. And I know the fact is that Facebook alone spend $120 million a year with Cisco just for their top-of-rack switching. So that's the next part that they want to reduce the cost of. So these are the vendors that support ONIE. So all of these switch manufacturers, if you look at their product list and their SKUs, you'll normally see two SKUs. You'll see one that says, so sort of the Dell S4810 example, it will be the S4810 part code that comes with Force 10 OS. And then they'll be listing another part code where the switch is just bare metal. It's got nothing on there apart from ONIE. And that gives you the opportunity to install other operating systems. And there's also people that don't use the Broadcom chipset in this example, such as Mellanox as well. And then there's us operating system vendors. And there's myself from Cumulus Networks here, and our competitors, Big Switch and Mellanox. But we've all had to put our differences to one side, really, and come up with a standard to get our operating systems onto the switches for the better good of the community. Because what we don't want to have to do is people to buy a switch and then sit there with their JTAG programmer, configuring the EEPROM and then TFTP loading the operating system, because that's no good for any of us. This is what a network switch normally looks like. Pretty standard design. On the right-hand side, you've got the switching ASIC, which has all the front panel ports connected. Maybe they're 1 gig ports or 10 or 40 gig. Then there's a PCIe bus hooking that up to a CPU. It's normally a single system on chip. It's got some RAM, some boot flash, and some mass storage. Sometimes in the case of like a CF card stuck in the box of a hot glue gun, or SD card on the side of the switch. And that SOC has a serial port and an Ethernet management port. And the bit we're concerned about with ONIE is just the left-hand side. We just want to get the operating system onto the flash, and all our content onto the mass storage. It's then the operating system's opportunity and role to handle the configuration of that ASIC to actually drive the installation. Your question?
Yeah. So in case of a top-of-rack switch, I mean that's relatively easy, let's say. In a chassis-based system, you would need to take care of like downloading microcode to line cards and etc., etc. So I guess we are far away from being able to do something like that.
No. You still, in some cases, you still need to download microcode onto the switching ASIC as well. That's a pretty standard operation. As you go through SDK bumps, for Broadcom, for example, those SDKs, when the next version gets installed and started up for the first time during that initialization process, it'll look to see what microcode is installed on the ASIC. So as you install your next release of the OS, maybe if the microcode hasn't changed, it won't need to do that install. So even in the same on chassis or top of rack, you still need to go through microcode upgrade bumps as a part of the course every year or so. In most cases at the moment, this CPUs have normally been a PowerPC. In most cases, a P2020 unit, like a single core 800 megahertz or 1.6 gigahertz processor. A lot of cases, they've got maybe 2 gig of RAM and possibly around 4 gig of storage. This is what happens when the switch leaves the factory with ONIE installed. So we have a low-level bootloader that configures the CPU, and that boots ONIE. In most cases, that's U-boot at the moment. Then ONIE has the Linux kernel with BusyBox. It'll bring up the Ethernet management port, and it will locate the OS installer, and that could be a variety of means that we can go through in a minute. And ONIE provides the tools to look after the storage and the environment for the installer. And then we grab the installer that we find over the network or on local storage, and then we'll execute that and install that onto the storage inside the chip. That's the switch even. Once the operating system has been installed, ONIE won't get started. We'll configure a setting in the EEPROM so the network OS is started straight away. ONIE is still there, but we can flip a bit in the EEPROM for it to kick in again. But normally we just boot straight into the network OS. And it's that network OS that will interface with the ASIC and run all the layer 3 and layer 2 protocols that you need and provide like a CLI or that management interface. So how do we go about doing network discovery and install? So we use DHCP IPv4 and IPv6. We'll configure the network interface. We'll grab DNS, server settings, search domain, and hostname from DHCP, or you can manually set it. And then we'll try and locate a network installer, and we do that via a variety of means. We'll look on the local file systems. In some cases, some of these switches are now coming with USB front-facing ports. So you might have an OS on a USB stick that you shove in there. Or in most cases, we'll look through DHCP options, where you manually set the file name, a bit like you specify the Pixie Linux install path. We'll do DNS service discovery. We'll look in multicast, and we'll look at your IPv6 neighbors. And then from those sources, we normally get given a file name, and it's that file name that we'll execute. And we'll also go for a waterfall, a bit like that you've seen on Pixie Boot. So we look at the. This is just on our on the website for this. So these are the methods that we try, and then we try to find the installer on the network. So we'll start off specifically with the architecture and the vendor in maybe Quanta or Dell and the model number, and then we start filtering down until we're just looking for ONIE-installer. And you can also specify the parameters as part of DHCP options as well. Are there any questions about the discovery mechanism? Okay, the question comes up a lot. Why not use Pixie? And that's because Pixie's not readily available on the PowerPC platform at the moment, and it hasn't got support for things like IPv6. And we're seeing one of our largest deployments is a complete only IPv6 data center, and they've got 5,000 top-of-rack switches. They've got no IPv4 on the inside. At the edge of their network, they have HA proxy boxes which have IPv4 facing out to the internet, and everything on their management domain is v6. We can use existing Linux drivers for the Ethernet management interfaces, and we don't need to write new ones. And it allows it to be really automated in a nice and easy fashion. So this might be a good time that we could. I'll put that there. I can show you a switch. So what I got, this is like a Mosh SSH session back to some kit in my garage at home. Hopefully cool, it's working. Okay, so this the tab on the far left is a IPPDU, so I can flip the power port on the switch. Okay. Cool. So the switch that I'll be working on is connected up to port 17. It's a Quanta LB9. So this is a 48-port 1 gig switch with 4 10 gig ports. And then we're just set. Cool. We just connect to the serial port that's also hooked up to that switch. And then this third tab is the management server connected up to the Ethernet interface. And this box is running DHCP, and it's also got light HTTPD on here. So inside the var www directory, you can see we've got some install files. So the first of those is the Cumulus Linux binary. It's about 80 meg. And then we've got a demo installer, which is just a really tiny, like a reference OS for ONIE that we provided to other OS vendors to show how to package their operating system. Then we've got a symlink for the ONIE-installer pointing at Switchlight. And then this is the Switchlight installer. And Switchlight is a network operating system released by Big Switch. Okay, so if we switch on that port, I'll back over here. So you can see U-boot kicking in on the switch, and it's starting up. So this box has got a 4 gig CF card in there. Okay, now Switchlight's starting up. So I think these units are, this box is only 800 megahertz in there. So the thing to bear in mind is the actual system on chip doesn't need to be that powerful in a lot of cases, because it's not actually forwarding packets. It's only sending instructions down to the ASIC, and it's that ASIC that will be doing the wire speed routing. So in this case, these boxes can do, they can route layer 3 at 960 gig a second. But it's not actually that PowerPC chip that's forwarding those packets. So this is Big Switch starting up. So it's just Linux. Their product does some crazy open flow stuff as well. It's just starting those agents up. So there we are. We're just at the login prompt for Switchlight, running on that Quanta LB9 in my garage back in Wales. So say we no longer want to run Switchlight on that Quanta box. Maybe it can't do OSPF unnumbered, or we want to run our own BGP daemon that we've written in Python, for example. So we can install a different operating system, and that's really easy in this case. So what we can do is we can just remove the symlink on here. And then we just link to the demo installer. So that's there. And then we just turn off the switch. And we power it back up. But before we do, what I'm going to do when the switch comes back up is start hitting enter during the boot sequence. And that'll drop me into the U-boot prompt. And from there, I'll start up the ONIE discovery routine, where it will go off and it'll go through the discovery steps here. And what it's going to come across is the ONIE installer file sat on our web server on the management subnet. Okay, so at the prompt. So you can just see this is just U-boot that started up here. There's very little about the box. So this is only starting. A very tiny Linux kernel that's going to start off onto that bash discovery routine. So all of the discovery for locating operating systems is just a set of bash scripts that we bundle up. So you can see that ONIE's got an IP on the management network, and it's discovered the installer file that we placed on the server. So you can press enter and get to the prompt. So you can watch this while it's happening. So it's erasing the flash on the switch. That's just going to, as part of the operating system, we have some checksums at the beginning of the file to verify it before we DD it back out. And now the switch is just booting. And this time it will skip ONIE, and it will drop into our demo operating system, which is essentially just a tiny Linux kernel with a bash prompt. So we now got a completely different operating system running on the switch, and that's what the functionality that we want to provide. We want to allow other operating system vendors to write operating systems to run on this open hardware that we're starting to see now. And in most cases, this is the hardware that a lot of people have already got in their racks. It's just that those switches have got a Juniper logo on the front or a Brocade logo. In most cases, it's normally, say for example, what we sometimes do is I open up all these switches on the table and I take the lid off, and if you look inside, you'll just see a P2020 CPU and the normal Trident Plus Broadcom chipset. It's in all the vendors, they just seem to lay out maybe their I2C buses differently, or they use different fans or power supplies. So what I do now is I just kick off the install of the next OS, and then we can go back to the slides. So again, we just change the symlink that it will look at. And we turn the switch off. I guess just got another IP, and it's going to go through the discovery.
So the reason you pressed return multiple times was to interrupt the boot up process, because else it would have booted from compact flash, is that right?
Yep.
Okay, so that's the way you basically change the OS, by getting into that environment and say, okay, boot ONIE again to load the new image onto compact flash.
We also provide some binaries that you can include in your OS, or just bash scripts that point you in the right direction of where in the EEPROM to change the flag for when it boots. For example, in Cumulus Linux, the OS it's installing now, we have some nice commands where you can type ONIE rescue or ONIE rediscover, and that will set those settings. So then you can just run, say, CL image install -i, and then you can just do reboot. But the -i is actually setting the EEPROM setting. But in our demo OS, we don't have that those commands there. And to be honest, the first OS we had on there, the Big Switch operating system that does OpenFlow, I've only ever installed that on switches. I have no clue how to use it. And we don't even know how to log into it. But we provide that rescue mechanism, so you can always interrupt the U-boot to get back in. The thing we don't want to do is have ONIE in the boot chain, because a lot of these big tenders and RFQs from large data centers, they specify the amount of seconds that they can wait from the time that the switch is powered up to forwarding packets. And if we added a 2 or 3 second delay there, where ONIE was checking for a keyword entry, that could push us over that barrier. So these are the different behaviors that ONIE provides. So we have a reinstall state, which is the one that I was running manually. and that allows you to remove the current OS, and it will go back to kind of a new out-of-the-box state. We can uninstall where we take the operating system off the flash. We can do a rescue, where it will just do the repair and debug. We do an update where you can use that to install a new version of ONIE onto the boot chip, and we have a diag function as well. And this is something that we're trying to push hardware vendors down the road of. So as well as them compiling ONIE to run on their hardware, we'd like them to provide a very small Linux network operating system that you can boot up to that will do some checks, maybe some loopbacks on the ports, and it can verify that the ASIC's in a good state. Because we find that can be very useful sort of for attack cases as well. So these provide all the mechanisms you need to get your OS onto the box, to be able to remove an operating system, to do recovery, and a hook to do diagnostics as well. So some of the lessons that we've learned in the past few years of developing this, even within the same CPU family, P2020, across all those different vendors, everybody will be laying stuff out differently. Different amounts of cache, different flash types. Everybody's changing stuff, even between the same SKU from some vendors. The boards will be changing slightly, and that's something we're trying to push these folk in Taiwan to do is to actually change the part code if the layout's changing on the board, because it makes a real difference for those of us that are developing operating systems. Hardware vendors need the freedom to change the bootloader as well, and we'd like them to push their changes back to GitHub as well. Some of them are kind of resisting that at the moment. We need that mechanism to allow the hardware vendor to bundle their diagnostics tool. And some themes that we see, a lot of people are now based on this TRV EEPROM format for storing settings. We've got a table of that on our GitHub site. And the common hardware designs, they can really reduce the time. So in most cases, you see that these switch manufacturers will just go to Broadcom and they'll pick up the reference design when they license the SDK. And all they do is just move, like I was saying earlier, move around some ITC ports and some power supplies. And those ones are great because it means the bootloader will go on there quick, and then you can install multiple operating systems. You don't have to be messing about where someone's changed from a CF card to SD between hardware revisions. So what are we up to now with ONIE? PowerPC, we're starting to see that kind of phasing out in the top of rack switch market. Everybody wants x86 now. So now we're seeing switches come along like the Dell S6000, which either have dual or quad core x86 chips on there, and that allows you to do a lot of kind of offloading some functionality into CPU that you can't do on the ASIC. So we've got an x86 feature set for ONIE, and we have a VM available to prototype that. We're also seeing some manufacturers think about ARM and even MIPS. And we want the behaviors of ONIE to be consistent across the different architectures. And we're working with some universities in the States to do to put together some OCP testing labs, so we can do a compliance sticker to give to the hardware manufacturers to say that they comply with this boot standard. And by doing that, it opens up the marketplace again for other people to get involved and develop network operating systems. So these are some of the new features we're actively testing and trying to get our V6 feature set fixed up. We're working on DNS service discovery and multicast, and this hardware vendor diagnostics tools. We do quarterly releases, ongoing maintenance, and we've had lots of contributions. So some of those vendors that I showed earlier, they've actively submitted patches. So if you're looking on the GitHub or our mailing list, one of the features that we didn't have was a function to store like a service tag, and Dell have those on everything. So they submitted a pull request on the GitHub site, and we accepted that. So what's our x86 strategy? We can use the existing BIOS that comes on the switches. In most cases, the switch vendor will license a BIOS from a kind of traditional BIOS company. During manufacturing, in the factories, we're going to have them install GRIB2 and our ONIE x86 release. And then the network operating system installer, if that's Switch Lite or Cumulus or maybe the FTOS release that's going to be ONIE compatible, will do the partitioning on the disk and it will install the software and keep the GRIB2 configuration up to date. So this is what the block layout will look like on the x86 boxes. We're going to have 4 partitions: a GRIB boot partition, the ONIE boot partition, the ONIE config partition, and then from partition 4 onwards, that's going to be free for the OS vendors to split up as they like. So in our case of partition 4 onwards, we're going to configure that as LVM and split it into 2 OSs, and then we can use snapshots to provide the ability for the user to roll back the OS. And so like we're going to use the GPT format, as it's kind of widely supported now. And it will allow you to switch between multiple operating systems easily. So the switch will just start to look like a server like everyone's been used to for a while. So we'll have these 4 standard install options. And then after you've installed the OS, the network OS will appear as the 5th option, but it'll actually be the default. So what does the network OS have to do? It's going to create the partitions, install the network OS into that partition 4 onwards. And then what we don't want to happen is for the network OS itself to be editing the GRUB files, because someone's going to screw up there at some point, and then you're going to end up with a box that you're not going to be able to do anything on. So we're going to provide these commands to the network OS, or wrapper scripts that they can bundle in, where we can at least sanity check values before they're written to the GRIB config. We have a website for ONIE, which is kind of separate from Cumulus completely. The GitHub site and the documentation is on GitHub pages as well. I'll flip back to this install. So you can see here, it went through, installed Cumulus Linux, and that's just taking us to the prompt. If my wireless can back up. Oops. Latency. Let's try again. I'll try flipping back to the different wireless. Okay. Alrighty. So it's finally into our network operating system. And in our case, oops, who dropped it? You can see on this PowerPC box, we cut the mass storage up into 2 slots. So we can have 2 different operating systems installed and flip between them. But we also provide a means, if you do climage select -I, that'll set the flag in the EEPROM, and so when U-boot boots next time, it'll drop into the ONIE rescue routine. Have we got any questions?
So one more. In terms of environmental stuff, so fans, speeds, and stuff like that, is that standardized? Or are only the switches that have the Broadcom reference design implemented?
I'll level with you. That's chaos.
Chaos.
Yeah,
I guess so.
So in some cases, you might find a standard Linux driver or something, or maybe sometimes we've seen like a one-wire bus inside the box. Sometimes the fans and the power supply voltages will be available on I2C. And that's down to the network operating system to kind of standardize and have an abstraction layer between that and the user. I know in our case, and maybe Big Switch, you can use like LM sensors. But we have to look at which hardware we're running on and use a different routine to access that. Any other questions? Either about ONIE or data center switches?
Repeat, please.
Sorry?
The last sentence is...
Oh, I can either answer questions about ONIE or data center switches or Linux on switches, any of those topics. Okay. Okay, I guess I'm done. I might have some spare slides that maybe you can... So this is the HCL of the different switches that we have ONIE running on at the moment. At the top, there's some 40 gig switches. And these are all in the 32 by 40 gig format. Those boxes they can route and switch packets at 1.6 terabits a second line rate on every port. As you can see, they're all the Broadcom Trident 2 chipset. The price point you see for those 32 gig by 40 switches is around sort of the $8,000 US mark. And then the 10 gig switches, a lot of cases they're 48 by 10 with the 440s. Or we're seeing these much denser boxes now, the 96 by 10 with 840s. And one of those is around the sort of 4,000 euros mark for the 48 by 10 gig. And then some of the smaller boxes, which we're starting to see people veer away from deploying 1 gig in racks now because of the 10 gig price point. They may be around the sort of 2,000 euros mark. But it's all of these vendors that we've been working with to get ONIE installed. And these are the ones that Cumulus Linux can run on, and then a subset of this, some of our competitors' operating systems can run on as well. Or like in the Dell case, you can always run that traditional Force 10 OS.
So those are all Broadcom reference designs. What about the Intel reference design? How far are they with the reference design, and when are we going to see switches with Cumulus OS on them?
On the Intel, I think that there could be other ASICs that we've been working on first, ones mentioned earlier, possibly like Mellanox. Mellanox have ONIE installed, but there's kind of a difference between the switches that support ONIE and the switches that support Cumulus Linux because the SDK is involved in our case. I can't talk about kind of dates, but it will happen shortly. One thing that could indicate that way is the Intel reference design that was submitted to the OCP Open Networking project as well. And I know there's a few big data centers working on those switches. I have one other slide here that I put in that some people ask about, and this is kind of how we hardware accelerate Linux and do the kind of the magic offload. What we have is a kernel module with a switch driver on the right-hand side that runs on our network OS. And that talks to the switching silicon, like you mentioned, is at the moment it's a Broadcom. It's going to be the Apollo, the Triumph, the Trident Plus, or the T2. And we sync the state of the routing tables, ARP, and VLANs, layer 2 and layer 3 ACLs with IP tables. We sync all that state from the kernel down into the ASIC. And that's bidirectional. So as you add a root into Linux, we take that and we push it down into the ASIC. So it's actually the hardware, the ASIC that's forwarding the packets, not the Linux kernel. And then as the packets are passing between the switch ports, we update the counters in Linux against those interfaces. So we create Linux interfaces, so when you log onto the switch, and you do ifconfig or ipadder or iplink, you'll see 48 network ports flash past you. And you just configure it like it's a Debian box, but with 48 NICs. And then on top of that, you can run the normal layer 3 tools such as Quagga or Bird that are pushing roots into the kernel. And little do they know that also happening in the kernel, we're syncing that state down into hardware. And then if you wanted to create, say, a VLAN that you normally do with conft int VLAN on the Cisco switch, you just create a Linux bridge. So you do brctl, add br, nat, and then you do add if, nat, swp1, swp2. And we sync that state again into the hardware to create a layer 2 domain with those ports in it. And on top of that, you can run daemons like msdpd if you still want to use an SDP. Or if you wanted to configure an access control list, like you do in Linux, you just configure it using IP tables, and we'll push that down into hardware and actually create a hardware ACL. And we do the same with layer 2. We create a layer 2 ACLs with EB tables.
So IP tables is just an abstraction for the ASIC.
Exactly, yeah. So we want to have in our OS, we want to have a really clean divide. We don't want to present any of the kind of SDK features directly to you. So you should just better simulate it with a VM with 48 NICs. But when you run that same etc network interfaces config or Quagga config on a switch, it's just hardware accelerated.
So I guess I can shoot myself into the foot if I program stuff into IP tables that can't be programmed in the hardware. How do I make sure that I get notified by the fact that it can't be programmed into the hardware?
So we have a hook on IP tables that won't let you add rules that aren't supported in hardware. So an example of that would be you could do layer 3 ACLs for forwarding, but you couldn't do masquerading in hardware because the ASIC doesn't support it.
And then you punt to the CPU, I guess.
But see, the issue with that, if we kind of flip back to, where did I have that picture?
Because I already see myself troubleshooting 99% CPU cases.
Yeah, so in this case, we try to push everything down into that ASIC on the right-hand side. But we simulate those ports in Linux as tap devices. So traffic isn't actually flowing there. You can run TCP dump and stuff on there. But the thing to bear in mind, between the system on chip and the ASIC, there's only actually a 500 megabit bus in most cases. So you could have this fantastic box with 32, 40 gig ports. And you think, oh, great, this would be awesome. I'm going to install HA proxy on there. Or I'm going to terminate all my PPP users on there or an OPVPN. But all that stuff's actually going to be happening in the CPU. And you'll be better off buying a $99 server on eBay and shoving a 10 gig NIC in it and hooking it up to a switch than trying to run CPU-bound apps. So running Linux on the switch is great for automation. You can build out your cross fabric really easily with use tools like Puppet and Chef, managing lots of VLANs, using tools like Quagga and Bird. But for those tools, those issues where you want to do lots of layer 4 and 7 stuff, you still need to run that in like a kind of classic x86 server. At the moment, until that changes when you see the system on chip move from current generation PowerPC with the 800 megahertz to possibly x86 quad-core or hex-core CPUs in the switch as well. And what we'd like to see is manufacturers increase the speed of the interface between the two. Some of the initial designs we've seen have still got a 500 meg bottleneck there. And it'd be really nice if they still had that PCI bus, but they actually flip one of the 40 gig ports, and they flip it back into the CPU as well. So then you can start running those tools on there. So you could do, like you're saying, maybe you want to run some natting or something that isn't supported on the ASIC. You might be able to run that on the CPU.
Just a question. We have seen in standard x86 servers where we run bonding,
Yep.
VLANs, and a bridge together to hook up virtual machines. And we have seen that when you go past 4 gigabits, the performance is not scaling linear.
Yeah.
Then we moved on to OpenVSwitch,
Yeah.
which is, you can saturate 110 gig link without any problems with few machines.
Yeah.
So how much code do you share, or have you solved the problem in Cumulus Linux itself? Can you explain a little bit, or disclose it?
So if you all the control is happening in Linux, but the packets are never actually hitting the Linux kernel. So I could have a Debian box with an 800 megahertz CPU that looks, to all intents and purposes, like it's forwarding 960 gigasecond of traffic. And the counters are updating because the packet is only flowing through here. It's never actually hitting the kernel. But you think it's hitting the kernel because we push the counters back. So in Linux, you could run collect D, and you see it look like it's actually forwarding, but it's like trick play.
So it's like the model in the OpenFlow. You remove the control plane from the data plane?
Yep.
Okay, I got it.
And you still configure it. So say you had the Linux, the KVM box with some bonds. So in our case, you create a Linux bond, and just as you would on a software router, we turn that into a lag, and you create all the bridges, and you just attach them. You create sub-interfaces like SWP 1.100, and you map it into the bridge. And you set it up just like it's your software box, but it's all happening in hardware, and the switch deprocess on the right-hand side keeps all that in sync. But there's lots of vendors that are doing similar stuff to ourselves and now trying to use ONIE to do that. So people like Pika 8 you might have heard of, or Big Switch, they've all got kind of a different take on it. And our view is we'd like to have that separation between the ASIC and the kernel and just have an abstraction layer. Cool. Are there any other questions for Rob? Wrap up. Cool. Thank you.